Welcome to the video lecture series of data structure. Our today's topic is binary tree representation. Hi, this is your instructor Janice Shah. So let's start with today's outline. Students, today we are going to learn about the binary tree representation using array, and then binary tree representation using linked list. Okay, so let's start with our very first method to represent our own binary tree using array. So here, if you can see that this is the binary tree definition. Okay, why I'm just repeating this definition again in this lecture? Because you just get the idea, because in the previous session we have seen lots of definition about the extended binary tree, 2-3 tree. Fine, so there are various types of binary trees are there. So what exactly, sir, do you mean by binary tree? Okay, can you understand that one tree or one node in a tree where one node contains maximum 2 children? Okay, where one node contains maximum 2 children, then that is known as binary tree. Fine. So now here, if you can see in this figure that root node A is there. Root node A is there. Now root node A on the left side, see, the child of A is O and F. The child of A is O and F. Okay, so what happens? The tree or the subtree becomes from O, that is known as your left subtree, and the subtree becomes with node F, that is known as your right subtree. Okay, fine. So it means when you can divide your tree into left subtree and right subtree in two different parts. See students, subtrees is equal to number of child node is equal to number of degree. I always told this in my lecture that subtrees, number of subtrees is equal to number of child node is equal to number of degree. Okay, suppose your root node, if you can see how many degrees for the root node A. Sir, root node A contains degree 2. Yes, so yeah, right or wrong? Fine, because there are 2 childs are there. Same like that. What is the degree of node G? Sir, it is 0. Okay, what is the degree of node L? Or sorry, node J? Sir, it is 1. So here you can see the maximum limit of child is 2. That's why it's a binary tree. So in a binary tree, students, we have two different scenarios, one for the left subtree, another for the right subtree. Okay, and the maximum degree for the binary tree is 2. It can be 0, 1 or 2. Fine. So let's start with the very first example, that is array representation of binary tree. Students, in my every lecture of data structure, I usually say this sentence that each and every data structure can be represented by two different data structures. Which are they? If you remember, the first one is array and second one is a linked list. Fine. So here we are going to represent our tree using array. So here it is our tree. A is our root node, then O, F, okay, P, L and Q. So the sequence goes like this: A, O, F, then P, L, Q. Okay, now tell me, what is the height of this tree? We already learned about this. What is the height of this tree? Students, height of this tree is 2. Height of this tree is 2. Okay, so for each and every binary tree, if height is 2, then how many total nodes can be placed over there? You can place maximum 7 nodes. Sir, how did you calculate it? Okay, students, it can be calculated like this: 2 raised to h plus 1 minus 1. Here you can see that the height is 2, so we can store maximum 7 units only, or 7 nodes only. Fine. So array size is 7. So the very first step you need to do is you just need to make an array with a size of total number of elements, because we already know that array is a fixed size data structure. You have to define like integer a of 5, integer a of 10. Okay, whether you want to use only 3 elements, but you have to define array with a maximum size of limit. That's why here height is true, so I need to set the array with size 7. Okay, so first I am just showing you one array. Just imagine this is my array. The array index starts from 0 to 6. Okay, remember this is not an algorithm, this is array. According to program, the array index starts from 0 to 6. That's why it goes like this, 0 to 6. Fine. Now, how to place the elements? Students, it is very much easy. It is very much easy. Just remember this sentence. First, you need to go at root node, then take a left and take a right. So, first you need to go to the root node, then take a left and take a right. Okay, so that's why my array starts from index 0 for root node A. So here you can see the root node A is situated at index 0. Okay, so we need to write root node A at 0 index. See, here it is. So now what happens next? Now remember this, students, here the root node is at index 0. Okay, now what about the rest of the nodes? Now see, first we need to take the 0 at the root node, then for the left child at 1, then right subchild at 2. Now just maintaining this sequence like 0, 0, 1, 2, 3, 4, 5, 6, 7. It goes like this. It goes like this manner. Now it is very much easy. See, let's the next element is start with O. So the O is indexed at 1. So I'm just placing O at index 1. Now students, next we have F. So F index is 2. You can see. Then F is placed at 2. Now next we have the P. So P index is 3. So we need to place P at index 3. Now next we have L. So L is placed at 4. Now see, is there any left child? Is there any left child for F? Yes or no? No. So should we need to consider that empty space? Yes, you have to consider that empty space. Just because this is array, it's a fixed size data structure, you cannot do anything else. Okay, so here you need to consider that empty space also, but don't write over there. So our fifth index becomes empty. Now move towards the sixth one. Our sixth one is Q. Fine. So such like the students, we can insert or we can represent our tree into array. Okay, if you can see that the fifth index is empty just because F does not have any left subchild or any left child. Fine, that's why students, our fifth position index is emptied. Now let me show you another formula. Students, we have two formulas to get the exact position of the element. Suppose here in array you can say that A is at 0, OA is at 2, F is at 3. Now if someone asks you that what is the left position for second index, so at second index we have F, at second index we have F. So our formula is that if you want to find the position of the array, if we want to find the position of the node in array, then the formula is 2 into P plus 1 for left subchild and 2 into P plus 2 for the right subchild, where P is known as position of the data element. Fine. So here if you can see that 2 into P, okay, for which node we need to find is for the second index. Okay, at second index we have node F. At second index we have node F. So 2 into 2 plus 1, 2 into 2 plus 1, okay, that becomes our left child. That becomes our left child. Now tell me, is there any node at left side? No sir, there are no nodes at the left side. Yes, you are right. So that's why that place is empty. Now how to get the right subchild of particular node? Formula is 2 into P plus 2. 2 into P plus 2. So it whole terms becomes 2 into 2 plus 2. So 4 plus 2 becomes 6. So now we can easily say that if you want to find the right subchild, for node F, then it must be situated at 6th position. Fine. So these are the two different formulas which I need to show you for the array. Okay. Now let's move forward. Another example for the array representation. So here is little big tree for you. Okay. Now can anyone from you tell me what is the exactly height of this tree? Okay. So height of this tree is 3. Okay. So now once again another question for you students, that what is the total elements or how many elements we can store in tree whose height is 3. Okay. So how to calculate it? We just need to calculate using the formula 2 raised to h plus 1 minus 1. So here it is, students. Here the height of the tree is 3. Total is 2 raised to h plus 1, 2 raised to 4 minus 1, it becomes 15. So with the height of 3 in tree, you can insert maximum 15 nodes. Fine. So here we can make array of size 15. So here are the array indexes and array representation 0 to 14, 0 to 14, and then let's start with the root node first. So here the root node is A, it's situated at the 0 position. Then we have O and F with us. It goes like the same as previous. O at 1, F at 2. Now the next, students, if we have P, L, J, Q. So I'm just going to insert easily P, L, J and Q. So all 6 elements are there. In this array, all 6 elements are there. Now what about the next? What about the next? So now if you can see that P does not contain any left child. Okay, so after level 2, completed level 2, now level 3. At level 3, students, we have only 3 elements. Okay, so first, after 6, what is the next index we can go? At 7. 7 is empty. See, just check it out in this figure. There are no elements at the left side of P. That means 7 is empty. So just place it empty. Now the next value is H. So you need to push H, or you need to insert H at 8th position. Okay, now what is the position for the next? Now next element is E. So you need to just insert E at 9. Yes, you are right, at 9th position. Now what about the next is 10. So L's right subtree must be at 10th position, but it is empty. There are no child at the right position of L. We just make it empty. Moving forward, the next, that is 11. Okay, we just do it. 11, then 12, 13 and 14. So total 13 and 14, both places are empty. At 12th position, we can place G over there. Okay, because there are no left subtree for J also. J has only right subtree, and that is G. So if you can see here, with the tree with the height of 3, we can add 15 elements. That's why I made an array with the size of 15. Okay, and just placed element according to it. Oh, now again I'm showing you the formula for that. That is, for P is equal to 5, that the position of J element is at 5. So we can easily say that the J left and right subtree must be at 11 and 12th position. Okay, so that's it. Now then, moving forward to the next topic. Our next topic is linked list representation. It is our last topic of today's lecture. So here you can see the tree. Okay, that is AOF, our very first example of today's lecture. That is AOF, then PL and Q. So AOF, PL and Q. That is, height of the tree is 2. But right now in the linked list representation, height of tree, it does not matter at all. Okay, what is the matter? Okay, can you tell me, have you ever listened the word node before tree? See, before tree subject or before tree lecture, have you ever listened this word node? Yes, if you remember, in linked list we use the term node. Okay, node means node contains 2 things. One is data, one is pointer. Fine, but here if you can consider the particular A as a node, then it contains 3 things. One is data, that is A is a data, and there are 2 different pointers are there. One is left pointer, another is right pointer. So each and every node contains right now 3 things. One is data and 2 pointers. One is LPTR and RPTR, and that's the concept of doubly linked list. If you can connect with me right now, that's the concept of doubly linked list. So students, here we are going to represent a node as a doubly linked list. So if you can see, if we consider a particular node, then 10 has 2 different pointers. One is left pointer, another is a right pointer. Okay, so let's convert this tree into linked list. Okay, so let's begin. First we have root node. So I'm just making a hierarchy of nodes. Okay, no A, then O, F, fine, then P, L and Q. Now tell me, A's left pointer is pointing at the left child node and A's right pointer will going to point at the right child of A. So it is very much easy to connect the lines. So first let's connect A to O, then A to F. So this is left, right. Again, O has left subchild, okay, that is P, and right subchild, that is L. Okay, very good. Now, next for F. Okay, F has any left subchild? No. So let's just connect right subchild. Okay, so right is Q. So this is a hierarchy of Linklist representation. Now, what for the leaf nodes? Okay, and what for the empty place of F? In array we have already represented that empty place at the position in array. Fine. Okay. Now what about the linked list, sir? Okay, then it is very much easy, students. Here in linked list, the empty place or the empty child, that is considered as null. So F does not contain any child at the left position, then it must point at null. Now what about the leaf nodes? Students, how many leaf nodes are there? Only 3. Which are they? P, L and Q. See, P does not have any nodes because it's a leaf node, does not have any child node just because it's a leaf node. So here the left and right both subtrees pointing to the null. Now for L, F and left and right both pointers pointing to the null, and same as for Q, left and right both pointers will pointing to the null. So always remember, whenever you are just representing tree using linked list, leaf nodes left and right pointer must be pointing at null position. Fine. So that's it for today's lecture. Thank you so much, students.